Brilliant. Okay, thank you very much. I am Karoline. I am also a CDT student. I am in the first year of my PhD here at the University of Lincoln. And I will be talking today about the use of deep learning for semantic segmentation of plants in 3D. And we've already heard a lot earlier today about how the introduction of agricultural robots opens up possibilities to automate the crop care in the field and also for in-field data collection. And in that kind of context, I'm looking at 3D perception for those agricultural robots. And more specifically, I've been recently working on the task of semantically segmenting 3D representations of plants into their different organs, as is illustrated here by color. So the goal is to understand the shape of a 3D scan so that we can identify which regions of the scan are soils or leaves or stems. And there exist a number of algorithms to do this, but they are mostly very elaborate procedures of manually tuned filters based on classical vision methods. And they often rely on very explicit prior assumptions about the specific crop, which means they don't translate very well from lab settings into the field. And they often also don't have any way of generalizing to natural variations in the crop. So as we've heard this morning, like a lot of students had the idea, how about deep learning? Can we use deep learning to address this problem? So given the appropriate training data, can I teach a machine learning algorithm to segment the plant without the need for manual tuning? Now, I have recently done some work on this, and I will also show you some results in a little bit, but given the audience that I have today, I was more interested in talking about how this question led me into a bit of an exploration of how we even represent three-dimensional data and which representations are suitable for machine learning, but more importantly, maybe which benefits different representations have for the agricultural domain. So I'll present a little bit what I've been reading recently, and I'm very excited to hear all your comments later in the Discord. So my train of thought was kind of in 2D imaging, deep learning algorithms are already pretty well established as the standard approach to semantic segmentation, and especially convolutional neural networks. They work really well, they're very well studied, but it is not straightforward to translate them into 3D space. And that is because CNNs take advantage of the spatial grid patterns of images, and they extract information about local shapes by sliding receptive fields along the grid at different scales. But the way 3D data is most commonly represented is not as a neat grid like this, but as point clouds. And point clouds are unordered collections of coordinates in 3D space, which can vary in size and also in density, as you can see in the example here. If we still want to apply convolution to this, what we could do is simply discretize the point cloud into a grid representation, which in 3D is called a voxel representation. However, I think for agricultural data, it's not very suitable because to capture the very fine details in complex objects like plants, we would need a very fine grid representation, which also maps empty space. And so they quickly become really large and they're not very memory efficient. And additionally, with any kind of discretization, you also run the risk of losing precision, introduction distortions, and so on. So I found this very interesting paper. Instead of relying on discretization, they work around this problem by using a multi-view 2D imaging approach. So they capture a bunch of 2D images from several positions around the plant, then use the CNN in 2D to perform semantic segmentation on each image individually. And then the images are projected into 3D space and combined into a point cloud. The semantic information from the different views is then integrated via a voting strategy. So this works really, really well. It's much less reliant on manual tuning than the conventional methods. However, this is only suitable to a lab because you have to really know exact camera parameters and positions. And it also assumes that you have perfect visibility from all camera angles. Obviously, we can't get that in the field. So recently, new network architectures have been introduced, which are specifically designed to accommodate for irregular structures of point cloud inputs without the need for any projection or discretization, and most prominently, possibly PointNet++, which was introduced in 2017, has since been hugely popular. However, it's been mostly, or maybe almost exclusively been applied to rigid man-made objects, very structured environments like in autonomous driving or indoor scenery. And there are very few applications to natural scenery or even plants, not least probably because we don't have suitable large 3D data sets, because annotation in 3D, as we heard this morning, is very difficult to do. But also it's kind of unclear how the network will cope with naturally extreme variations in shape and the non-rigid nature of plants. So I recently did an experiment on this. I applied the PointNet++ network architecture to the plant segmentation problem and attempted to learn to predict point-wise segmentation labels directly from the point clouds. Now, in the interest of time, I won't go too much into detail here, but this is a project I'm still currently working on, so do please contact me if you're interested to hear more about this. I'll just give the very brief version. Because I didn't have a very suitable large-scale annotated data set of agricultural data available, I procedurally generated a synthetic data set simulating the in-field conditions. If you imagine that an RGBD sensor could be mounted to a robot that traverses along a field, and it would capture images from different viewing angles with realistic occlusion patterns. So these point clouds you see here at the bottom of the screen, they are actual examples from my data set. So you can imagine that's the data I trained my network on. And in short, I mean, there's a lot to it, but in short, it works. There's some room for improvement, but on the whole, the network achieved a mean intersection over union score of 0.719, which is actually comparable to other applications of PointNet++. Here you can see some predictions that my network produced along with the ground truths, and I've also highlighted where points have been misclassified, so you can compare a little bit. So yeah, there's some room for improvement, which I will address in the future, but I guess the brief summary is that the network learns to produce sensible semantic annotations. I've also recently validated these results on some real-world data, and this is kind of just to demonstrate a little bit that the concepts about local shapes that the network learns do transfer to real-world data. So this is, on the left, we have 2 tomato plants, on the right, it's a maize plant taken from real plants in the lab. And I feel like the annotations are pretty sensible. And this is considering that this data differs from the training data, not only in how the sensors were set up, but also it was recorded at a different scale. And I mean, it includes an entirely different species, and yet the network seems to have some understanding of what a stem is and what the soil is. So on the whole, I feel like this is a potential alternative to the state of the art. I will further explore this. Obviously, it will need some further testing with the real world training data when it's available. But this, I feel, is especially suitable for larger scenes that have maybe already been assembled from multiple views. If we are looking at point clouds that are produced just by a single recording from most depth sensors, there might be an easier way to think about the data rather than point cloud representation. So I recently found 2 very interesting papers. The first one here, in this paper, they use an RGBD sensor, but instead of using the point cloud representation of that data, they think about the data more as a depth image or a depth map. Because the data is captured from a single point of view, it does also sort of form an image grid, which allows for the use of CNNs. And in a similar way, RangeNet also exploits the way that points are recorded by rotating LiDAR sensor. So instead of learning on the full unfurled point cloud, you can imagine that they unraveled or flattened it to also form a sort of grid-like structure, and then they learn on that spherical projection of the point cloud. So this all inspired me to be a bit more creative in the way I think about 3-dimensional representation. And I guess my main takeaway is that for the next steps of my PhD, representation will be really crucial, because I want to start thinking about building dense maps of crops from single scans. And I've listed some other representations here that I haven't had the time yet to explore, but I'm really interested in. And I also want to find out at what stage of and in what representation I can best extract semantic information from the 3D representation of plants. So with that, I will leave off now, and I'm really excited to hear all your comments and questions later.